we're now going to find indefinite integrals that have kind of a quote constant multiple inside the function, like this here. Here's an example. So notice this is the cosine of 3x. So 3 here is kind of a constant multiple that's on the x value. You know, you put it on the x value before you put it into the function. Okay, so I call that like a constant multiple inside the function. Now if it were a constant multiple on the outside of the function, then what we learned is you can just pull the constant multiple out and take the derivative of what remains. Okay, but you can't necessarily do that when it's on the inside of the function. In this case, you can't pull the 3 out of the cosine, and so therefore you cannot pull it out of the integral. Okay, and so can we find the indefinite integral of cosine of 3x? And the answer is we can. This is actually not that difficult here. So think here for a moment. The sine of x is what gives you, the derivative of the sine of x gives you the cosine x. So let's consider taking the derivative of the sine of 3x. Okay, so in this case you would have to use the chain rule, right? It's the derivative of the outside function, which would be cosine of x, evaluated at the inside function, which is 3x, but then it's times the derivative of the inside function, and so the derivative of 3x is just 3. So you would get this here, so you could rewrite that as 3 cosine of 3x. So when you have a constant multiple that's inside the function here, okay, the antiderivative here of sine of 3x, what would normally be the antiderivative of just cosine of x, when you take the derivative, what you're going to get is this with the constant multiple out front. Okay, and so what we can do is we can do this. So let's say I have the derivative of cosine of 3x inside my integral. Okay, and I know that the sine of 3x gives me this derivative. So if I had this inside here, if I had a 3 there, then I could go backwards and go back to sine of 3x. But I don't have a 3 there. Well, if I don't have a 3 there, I can make a 3 there by doing 3 over 3, right? And so, and this would be like the cosine of 3x dx. And because this is a constant multiple, what I can do is I can pull the 1/3 out. Okay, I can pull a 1/3 out, and I'm left with just 3 cosine of 3x dx. And now I have this, and so I can go backwards to this. So this would be 1/3, and then the antiderivative of that would just be sine of 3x, right, plus c. So this would just be 1/3 sine of 3x plus c. Okay, so if you have a constant multiple here, okay, basically the idea is, because of the way the chain rule works and that the derivative of 3x would just be 3, what you're going to get is you're going to get what you would normally get for the antiderivative of just cosine of x, right, evaluated at the 3x, but then you have to have a 1/3 out front. So this 1/3 out front is just the 1 over whatever this is. It's the reciprocal of this. And the reason is so when you take the derivative of this, like this, and you have that 3 there, this 1/3 will cancel that 3 out, leaving you with what you would have inside the integral here. Okay, so basically, and you can just set it up like the way we did here. If you want to, you can do 3 over 3, pull the 1/3 out, and then you'd be good to go. Or when I see integral like that, so if I saw, like, let's say tangent of 5x dx, I know the antiderivative of tangent is secant squared. Okay, actually, I just did that wrong. I don't know this antiderivative, so let me write one that I do know. So let's say I have secant squared of 5x dx. And so the point here is I know the antiderivative of secant squared is just the tangent of x. So what I can do is the constant is 5, so I can put a 1/5 out front and do the antiderivative of just the secant of x, but have it evaluated at 5x plus c. And the reason I have the 1/5 there, so when I use the chain rule on this, and I got the derivative of this, which is the secant squared of 5x, times the 5 would cancel out with this, leaving you with just what's inside there. Okay, so it's basically finding the antiderivative just like you did before, but you're putting 1 over whatever is here in order to counteract that 5 there, so that you're left with this. Okay, so let's do one maybe that's a little more tricky. What if I had something like we'll say the derivative of we'll say 2 sine of we'll say pi over 12x dx. Okay, so what I would do here is I would probably pull out that 2, okay, and then just be left with this. And then I'm going to do the antiderivative of sine is the opposite of cosine. So I have 2. It'd be the opposite of cosine. And it would be at 12 pi over 12x. But then out front, or I'm going to put it behind here, I need the reciprocal here in order to counteract this. And so I could rewrite this whole thing as the 2 here would cancel out. So I'd have like negative 6 over pi. And then I'd have the cosine of 12 pi over 12x plus c. So I would have this. Okay, you would have, basically doing the antiderivative of just the sine here, but it's evaluated at that, and then I had the reciprocal here, okay, and I also had the constant multiple out front to deal with. Oh, and you know what? When I made a mistake. This would be 24 here. I would have 24 on the outside. Sorry, I'd take this constant multiple times that 12. So negative 24. So it'd look like that, okay? And we could take the derivative just to double check it here. So it'd be, we're going to have negative 24 pi cosine of pi over 12x plus c. Okay, and so this would be, you'd have that constant multiple like that, and then I'd take the derivative of the cosine, which would be the opposite of sine, evaluated at pi over 12x, times pi over 12, and then the derivative of the c just goes away. And then when I simplify this, I can do it up here. When I simplify this, this pi would cancel out, and then the 12 would, the negatives would cancel out, and this would just become 2 sine pi over 12x plus c. Okay, and I barely fit it in there, so I'll write it here. 2 sine of pi over 12x plus c. Okay, so hopefully I think this makes sense here, kind of what I'm doing. What you could do is you could maybe make a rule where if you had this of some k times x dx, then what you would get is 1 over k capital F of k times x plus c. And this is where the derivative of f of x would equal the original function. So in other words, the capital F is the antiderivative. So basically you just have that 1 over k, so that when you use the power rule here, okay, so I can, let me actually take the derivative of this 1 over k capital F kx, and not the power rule. I'm sorry, when you use the chain rule on this 1 over k would cancel out. So you could pull out the 1 over k, and then you take the derivative of the outside function, evaluate it at the inside function, times the derivative of the inside function, which is just k, and then the c would go away, and then this would cancel out that, and then the derivative of f of x, or f of kx, is f of kx, which is what you put in there. Okay, so that 1 over whatever the constant multiple is does kind of counteract that. Just so you know, if you have a derivative like this, let's say I have 1 over square root of 2x minus 1 dx. So this is a linear function, but notice the derivative, and this would be like an inside function of 1 over, let me rewrite this as a power. So this would be like 2x minus 1 to the negative 1/2 dx. So you can use the power rule, but that inside function is like a constant multiple, because the derivative of 2x minus 1 is just 2, just like the derivative of 2x is just 2, right? And so you can still use the rule I use, just evaluate it at 2x minus 1, but that minus 1 doesn't change anything on the outside. So what I can do is use the power rule, where, I can use the power rule on the overall thing, and I just have a 1/2 out front, and then this would be the 2. If I add 1, I would get 2x minus 1. Adding 1 of that would be 1/2 all over 1/2 plus c. So I'm using the power rule evaluated at this, and then this 1/2 is my reciprocal of that constant multiple in there. And so then it turns out that these actually cancel out, and I would just get the square root of 2x minus 1 plus c. Okay? And then we could actually take the derivative of that. Right? This would be the derivative of 2x minus 1 to the 1/2, and so I'd bring the 1/2 down, and then I would have 2x minus 1 to the negative 1/2, but then I'd have to take the derivative of the inside function, which is 2, and so again these cancel out, and you're left with 1 over 2x minus 1 square root. And so this is equal to that up there. And so in other words, this power rule can really be generalized to, if I had something like f of ax plus b dx would be 1 over a capital F of ax plus b plus c. And this is where again, the derivative of f of x is equal to little f of x. So in other words, you can generalize that power rule for when it's a linear function, okay, like that, with just the 1 over a, because the derivative of ax plus b is just a. Let me also show you one other thing too, and that is, what if you had a regular exponential function? So we can say, what if I have like 5 to the x dx? Okay, the point here is I could rewrite this as e to the natural log of 5 times x dx. And so really you have e to, and inside of this you have natural log of 5 times x. This is really just a constant times x, and the derivative of that would be the natural log of 5. Okay, it's just another constant. So really what you have here is a constant multiple times x. So I could rewrite this, so I take the derivative of the outside function, which is just e to the x, raised to the natural log of 5 times x. But then you would need the constant multiple here to cancel out. You'd have 1 over natural log of 5. And I could have that out front or whatever, plus c. So you could rewrite this, 1 over natural log of 5. And then this here would reduce down to 5x plus c. Okay, or if you wanted to, you could write it 5x over the natural log of 5 plus c. And you could generalize this to, if you had a to the x dx, this would be equal to a to the x over the natural log of a plus c. Okay, and that would be taking the derivative of any, or taking the integral of any exponential function, even if it's not e to the x, because the natural log is just a constant, and so we're using this constant multiple. Okay, now if it's more than a constant multiple, then you can no longer do it. And the reason is, if you look back to this original one that I did when I showed this, is in order to get that, so the sine, I had this, but if I took the derivative of sine of 3x, I got 3 cosine x. So if I had a 3 out there, then I could take the antiderivative and get the sine of 3x. And so what I did there is I put the 3 there by taking 3 over 3, okay, and then I could pull out the 1/3, and then I had the antiderivative, okay. So the reason this works only with a constant multiple is that you can pull out a constant multiple, okay, and then that way you can get the constant multiple that you need there, and this is where the 1 over the constant multiple comes from, and then you just do the antiderivative. So it only works with the constant multiple. But what we're going to do is, this is basically a special case of the substitution method. And so there is techniques where you can do other things with other functions using a substitution method. And it would also take care of this as well. But this is just kind of a special case of that. So in the next section, what we're going to do is we're going to look at the substitution method.